Okay, so this is my arc length project. So I'm gonna try to make this as quick as possible. I'm sorry if the presentation's a little bit long. I'll try to make this as quick as I can. So basically the backstory is there's a lot of things people hate. There's politicians, nobody likes them. There's Brussels sprouts, they taste bad. There's inverse trig derivatives, nobody remembers them. So there's a thing that I hate that's not part of these, and I feel like more people should be aware of the really bad part of these. The tall buildings. Tall buildings just aren't great. I can't tell you why. I just don't like them. I think they're safety hazards. I think that's probably the reason. So moving on. Basically, there's some couple of tall buildings. For examples, there's the Eiffel Tower. You could be up here. It's like a safety hazard. If you jump off, you probably die. Same thing here. You jump off, you probably die. But I mean, I guess you can make the argument with this building is that the people living here, it's kind of housing people, which would be cool. I mean, I would probably put it on a pretty, that makes it pretty cool. But I found a picture of Will Smith on top of the tower, and I feel like if he fell, he'd probably not survive. I don't know if Will Smith would survive that. I'm not sure. I'm not a source, but I don't think he'd survive. And I think that's pretty bad. So it's a safety hazard. And basically, the one that I want, the closest tall building to me is the Empire State Building, and I feel like we can make a real difference here. Because if we take the Empire State Building, right, and we somehow repurposed it so it's not vertical, like we don't have to relocate the Empire State Building, waste all this material to make it. We can just pick it up and move it somewhere else horizontally, so it's no longer a vertical hazard, So basically, what I want to do is I want to take the Empire State Building and put it in the middle of the lake in Central Park, so we can have a bridge, and then from that bridge we can have a walking path, which is, or we can have an easier path through the lake than the normal walking path. It'll probably be a little bit quicker. I mean, well, it will be a little bit quicker because it's just gonna be a line. So that's my plan. That's my basic plan. Here's a diagram of the plan, a very professional diagram. This is an aerial view of Central Park. This is where the bridge will be, approximately. So instead of going all the way around this way, let me get the pointer, wait. Instead of going all the way around this way and making this entire journey, when you're over here and going to this part of the bridge and you want to go on the lake and you want to go around the lake, you can just go across the tower, across the building, and we can do that. So just to conclude this, I mean, I calculated it. This is the distance. This is like 1357 feet, and that's within the range of the Empire State Building, so it'll fit completely fine. This is the original path that you want to take if the bridge wasn't there, and this is the path including the Empire State Building, making it a bridge. So we want to figure out how much more efficient this path is than this path, which we can do, but we have to figure out first the length of this path, which is where we have to use the arc length formula. So I made a basic diagram of, well, in the Google Maps tool thing, I made a path through the lake, and basically what I wanted to do was I wanted to label these points A, B, C, D, E. This part of the graph is one polynomial that I'm going to use to approximate this path. E to E1 is its own line, so I don't really need to use arc length for that. You can just find the length of the line. E1, D1, C1, B1, and A1, these are all the second polynomial that I want to use to approximate. And I have two separate axes, or two separate sets of axes, because it just makes it easier for me. There's the x-axis, and there's this is the original y-axis, and this is the x-axis over here. So A, B, C, D, E will all be in relation to those axes. But E1, D1, C1, B1, and A1, it'd just be kind of annoying to have the numbers all the way up from here, from this axis. So I made a new axis over here. It'll be the same because it's the same function. It's not stretching or anything, so the length should be the same. The only problem is I have to make all these values negative. So if this is the axis and B1, let's say, is 10 feet away, we would say that the B1's x value is negative 10. I'll show you the points the next slide. So the points of the first polynomial that I want to approximate are these ones right here. They're all positive, and this one's they're all y values are all positive, but the x values are negative. So the way I found the polynomial for these things right here is I use polynomial regression because there's 4 points. I use there's 5 points including the origin. So I use for both shapes. So I use like a I guess you would say quartic polynomial regression, and that got me this is the formula that we would need to use to find the full length of the new path. So this is the length of the first polynomial, length of the second polynomial, and then the length of the line. So to find this length, we need to use arc length, and to find the polynomials first, I use polynomial regression to get these formulas. I just use some calculator online to get these. There's a different variable here, a. This is basically just x, but in a couple slides I made a Desmos representation of the path, so I just needed to use a translation. So I just made this a. This won't change the derivative at all. This will just change the translation between the things. Because if you did plot product power rule, and then you just did chain rule for a because a is a function of x, it would just end up being like 1, so it wouldn't change the end product. So the function between the line is pretty straightforward here. All these endpoints are found with the tool on Google Maps to find the length. So the formula for the full length is the arc length formula for the derivative of the first function from 0 to 224, which is the last point, plus the arc length formula for the second function, the derivative of the second function squared. So that's for the second, that's the length of the second parabola. And then I just found the distance between the two endpoints of the lines, or the difference between those, to find the length of the line. So once I plug this all into Desmos with these functions, and I plug the derivatives in, I didn't do by hand, I just let Desmos do them, but they're just power rule. So I'll just do power rule for all these derivatives. And I plugged into the calculator, and I got this for the full length. So this is the Desmos representation. I just had a translation for a. It just adds a negative in front of all the terms, but that's fine. It doesn't change the length, arc length of anything. It doesn't dilate or anything, so it keeps the arc length the same. So this is the first path. This is the first polynomial. This is the straight line. This is the second polynomial, and this is the final length. So if you want to figure out the difference in walking distance from my plan, the original path, as we just calculated, is this much. So it's 1540 feet, and the next the path you would have if you just made a bridge straight across the Empire, like they put the Empire State Building in the length, it'd be 1357. So the difference between it is 183 feet. So you're saving 183 feet of distance going across the new bridge that we will put on the middle of Central Park. And you're going to save a lot of time. And I think if we just do this and we repurpose the Empire State Building in this way, I think it'll benefit a lot of people. It'll also decrease the safety hazard risk. My goal is to take all the tall buildings, so you see these couple ones in the back, and just make more bridges in other places because they're also safety hazards. So I think this will be pretty useful. I think this path is pretty telling. It's 200 feet savings. But yeah, that's the project.